application, and this application may choose UDP for transport protocol rather than UDP, because the UDP offers fine application control than TCP of what and when data is sent in segment. Why? Right. Can you explain the reason? And first one is, why does an application have more control of what data is sent? Can anyone tell me? What is the reason an application, so if an application choose UDP rather than TCP, right? Maybe because the UDP offers fine application control than TCP of what the data is sent. Right? Well, then what's the reason? Why? All right, so you can refer, if you look at the lecture note, you can refer to page 4. I can refer to page 4, and you can see the TCP sequence structure, right? And then you can find in TCP, besides the content, there is lots of control flags in TCP structures, such as the receive window, something like that. That means in some case, if the TCP protocol itself detect the traffic is too heavy to send, and it will just get more control of what data is sent, right? It will cut, sometimes it will just chop the data into different blocks, and then put the data trunk into different packets. That is one of the cases, right? So that's why we say TCP has more control on what data is being sent, which means the user has less control to decide what data is being sent, right? If you're using TCP. But the thing is, TCP ensures that all the data that's being sent will be eventually successfully received on the receiver side, right? Which means that's what we call the reliable connection, right? So there's more control. Sorry, the user has less control on it. So the user has less control, right? But for UDP, of course, the user has more control on what data is being sent, but UDP doesn't do anything. UDP doesn't guarantee that all the data you have sent it will be eventually received on the receiver side, right? So users has more control. User. All right. Of course, for the second one, if we talking about when the data is being sent, that's the same, right? You can refer to section 38. And you can see that TCP also offers the flow control and the congestion control, right? So there's flow control or congestion control, right? That is to say, if the TCP protocol detects either the traffic is too heavy, or the inbound transmission rate on the receiver side is too heavy, it will offer a flow control and congestion control to tell the sender not to send, so to stop sending, right, or not to send too fast. In that case, the user has less control to decide when the data is being sent, right? It is the TCP itself to decide when the data is being sent. So the same, a user has less control on when the data is being sent, and UDP. But if you're using UDP, a user has more control, right? All good. Right, so let's move to the next questions. This is more, the second question will be more important here because that is, I guess that could be a one of the patterns that will be quiz in the final. Okay, so you got two hosts, host A and host B, and they're communicating over TCP connection. So let's just draw a host A here. All right, and it's a host B. And this is the timeline, right? The time. We just make a vertical. And it said host B has already received from A all bytes up through by 126, which means sorry, it's true. Which means host A has already sent the packet to host B, and host B has echo back a response back to A, where the first packet, the sequence number of the first packet equals to 1, and the size equals to 1 to 6, right? So ACK here equals to 1 plus 1 to 6 equals to 1 to 7, right? And up to this point, aside from this point, right, is that host A then sends two segments to be back to back. We use different colors. This is first one. This is second one. Two segments back to back. And the first and second segment contains 80 and 40 bytes of data respectively. So the size here is sorry. The size here equals to 80 and the size here is 40. And in the first segment, the sequence number is 1 to 7, right? Of course. 1 to 7. The source port number is 302. Okay, 302, and destination is 80. Host B sends a ACK whenever you receive a segment from A. So question 1 is in second segment, so the blue one. The second segment sent from A to B. What is the sequence number, the source port number, and destination? Can anyone tell me what is the sequence number here? Anyone? Hello, anyone? Can anyone tell me what is the sequence number here? Yeah, obviously. 127 plus 80 equals to 207. All right. And of course, the source port number is 302, and destination port number is 80, because that is being sent from A to B, from left hand side to right hand side. Right? Okay, pretty easy. Okay, so now question B: if the first segment arrives before the second segment, in the act of the first arriving segment, what is the act number, the source port number, and the destination port number? Right. So the first one arrives before the second one, and so as long as host B receives the first one, it will send a act back to A, right? And can anyone tell me what is the act number for this one? What is the act number? Yep, the act number is 207. And what is the source port and what is the destination port? It is 207. Yeah, right. The source is 80 and destination is 302, because this the other way around, right? Okay, so now right, so third is if the second segment arrives before the first one, that means let's get rid of this first. Okay. Okay, let's assume that the first one somehow getting lost or getting stuck. And the second one arrives before the first one. And of course, as soon as host B receives these the blue packet, they will echo back the response. And what is the act number here? Can you tell me? Someone said 247. Is it 247? No, 247 is wrong. The answer is oops. What is the answer? 247 is wrong. Can you tell me what is the answer? Why is 167? What is 167? This the answer is 127. Why is 127? What's the reason? 127 is correct. Okay, so let's ask you guys. What is the physical meaning of the act number? What is the physical meaning of a act number? So what does it imply? So right. So once the host A see the ACK number equals to 127, that means that implies that host B is trying to tell host A that tell the fact that I'm still waiting for byte 127 and onwards, because the second one getting lost. So all the bytes from 127 to 207 is still missing on host B. So host B will send a packet where the ACK equals to 127 back to host A and tell host A to send the bytes from 127 again. Does it make sense to you? Yeah, because the green one getting lost, right? Then you have to imagine that, like, how do we deal with this case? How do we deal with this case to tell the host A to resend the green one? Because this is TCP connection, which means all the packet has to be eventually received by host B. So it doesn't allow any lost, any data loss, right? So that is how TCP will handle the data resend. All good? Okay, let's move to the last one. Okay, so the last question is suppose the two signals sent by A arrives in order. Okay, so let's remove this. Remove this. Okay, so two segments sent by A arrive in order, right? So the first ACK is lost, and the second ACK arrives after the first timer's timer interval. So that means once this one getting lost somehow, right? And where the ACK number equals to, of course, equals to 207, and the second one has been received by Jose. And now, can anyone tell me what is the ACK number for this one? So let's also draw the timeout here, right? So you can see the timeout is somehow in here, right? And up to this point, so on this point, host A will resend the green packet where the sequence equals to 127 and size equals to 80. And host A received the blue one, the blue ACK, after the first timeout interval. So can you tell me what is the ACK number here? Yep, 247. Right. Okay. So what is the ACK number for this one? What is the ACK number for this one? You sure it's 207? Someone said 207. Someone said 247. Which is correct? Which one is correct? Yeah, someone said 127. Okay, so we've got 3 options. I'll give you guys 30 seconds. Let me know. Just tell me which is correct. All right, I'll tell the answer. 247 is correct. Why? Whoa. B has received the bytes from starting from 1 to 7 at this point, right? Yes, you're right. Because all bytes up to 247 are received already. Are already received. Right. That is why Hostbit will send a packet to A, telling A that I'm waiting on all the bytes starting from 247 and onwards. Right? All good? So these two are wrong. All good, right? Okay, so let's see any question about this type of questions, because I'm pretty sure this one is very important, and maybe it's most likely will be being quizzed in being tested in the final exam or something. But I'm not sure like in what kind of questions that will be tested, because all you need to do is to draw this kind of the diagram based on the description, right? So you need to be able to draw the diagram based on the all the description given to you. So including the you got 2 hoses on the left hand side and right hand side, and uh, you need to point out the source port number, destination port number, and you need to point out all the packets being sent in between from left hand side to right hand side, and all the response backwards. And you also need to point out the sequence number, the ACK number, and the size of the packet as well. And if the question said if some of the packets getting lost or getting disconnected somehow, and you need to draw the cross to indicate that. And also you need to handle like how the packet is being sent between. All right. All good. So if you're not if you're not that familiar with this kind of question, I recommend you to go through this question later. Right. All good. Can we move? Okay, so next, okay, so Jose and B are directly connected with a 100 megabit per second link, and there is one TCP connection between the two Joses, and Jose is sending to host B and a file that's very big. So over this connection, and Jose can send his application data into his TCP socket at a rate as high as 120 megabits per second. But the thing is, host B can only read out of his TCP received packet at a maximum rate of 50. So Jose, host B, the link in between, and the outbound bandwidth is 120 megabit per second, and the inbound bandwidth is only 50 megabit per second, and this is 100 megabit per second. All right, so describe the effect of TCP flow control, and you can refer this to lecture note, I guess is on page 9 to 12. Right. So in the case that the bandwidth of the receiver side is much smaller than that of the sender side. So that is that is the time we come to the receiver window. Right. IE window. Right. If you look at the TCP segment structure, on the fourth row, you can find there's a field called receive window. And how do we use this? So how does TCP use this flag? So whenever the receiver doesn't want to receive anymore due to the buffer has been run out, it will set the receive window equals to 0. So set this to 0. And the sender will stop sending as soon as you receive the response where the receive window equals to 0. Right. So the receiver will set the receive window to 0 and send this packet back to A. As long as A receive a packet where this one equals to 0, the sender will stop sending anymore until it receive another packet where the receive window set back to some value greater than 0. All right. So if this one is set to a value which is greater than 0, and the sender will the sender will continue to send, right? And this is how the flow control is being handled in TCP protocol. Okay. So there's a receive window. All good? Any question? All good. I think it's pretty straightforward here. So can we move? Right. Next. Now we consider network shown in scenario 2. Okay, so let's just ignore the first sentence because we don't have the diagram here. So let's just draw for you. Let's just draw one for you. So that is all right. So this is a roller, and you find this. Of course, there's a buffer, right? So this is a roller. So this is the outbound. This is the inbound, and of course, you got a buffer in the roller where there's lots of packets being queued inside, right? So lots of packets that's queuing in the buffer, and now we suppose the timeout is a fixed value. And question A is asking you to argue that increasing the size of the finite buffer of the roller might possibly decrease the throughput. Can you explain why? Well, of course, if you want to increase the throughput, you would say, why not just increase the size of buffer and then let more packets, right? That is the more straightforward idea you can come up. So, but the reason is that if you increase the size of the buffer here, it might possibly decrease the throughput. Why? Can anyone explain to me? Right, yeah, kind of. That is what we call the packet. Will be what we call the prematurely timeout. What is this? That is to say, if you increase the size of buffer, for example, and let more packets come in, but bear in mind that the timeout is fixed. The timeout value is fixed. For example, 1 second or 3 seconds, right? Then what if the timeout has been reached, right? If you reach a timeout, but if you got like hundreds and thousands packets that is still in the buffer, so the sender will resend the same packet to the receiver. That means at the same time, like for example, you can imagine that at some point, there are two packets where the content are exactly the same in the network. That makes that causes the redundancy, which decreases the throughput, right? Because the queue is too long. You increase the size of buffer, making the queue too long. That means it takes the packet, it takes each of the packet in the queue too long to be sent or to be pushed in the channel. So that makes a loss of unnecessary redundancy in this network, which decreases the throughput. Right? All good. So that is what we call the packet will be prematurely timeout. Sorry. Okay, so now in the first question, we consider that the timeout value is fixed. And we know that if we fix the timeout value while increase the buffer size, that may decrease the throughput. Then now we try to we try to allow the host dynamically adjust the timeout value, right? So now the host are able to dynamically adjust the timeout values based on the buffering delay at the rollout. Will increasing the buffer size in this case help to increase the throughput as well? Can anyone tell me? Anyone? So now the timeout value is dynamic. In this case, can we increase the throughput? Can we increase the throughput by increasing the size of the buffer? Yep, you're right. So if the timeout value is dynamic, yeah, the throughput can be increased. However, what? The queuing delay will be very large. Yeah, you're right. Imagine that you increase the buffer size to infinity. That means you probably allow as many as packets coming in as possible, right? So now then, also the timeout value is dynamic. So it takes each of the packet queue much more time to go to the channel, right? Because theoretically, the size of the queue can be infinity, right? So the data would be very large. All good? Any questions? So you increase the buffer size, you allow as many packets in as possible. So the queue delay will be very large. All good, right? Can we move? Okay, so the last question is really much this is optional question, and it's all about mathematics. I'm not gonna go too deep in this question, and if you want to get more precise with this, you can come over to me, but I will tell you how to do these questions. So for the first question, for the first and second questions, you need to refer back to the tutorials last week, and remember you got we've got two equations to compute the utilization and throughput rate. We've got, if you revisit the tutorial last week or the lecture note last week, you can find that these are. Oops. Oh, my Apple Pencil is about now low battery. Okay. Okay, so okay, I can do something like this. I'm gonna stop this one and I'm trying to share my screen here. Right. So if you revisit the tutorial last week, you can find this equation, right? The utilization equals to L over R divided by RTD plus L over R. And now we've been aware of all the values here, right? R equals to 10, so this is R. And propagation delay is 10, which means RTT equals to 20 milliseconds. Sorry. Say, and we also got the L, which is 1024 byte, and of course you need to convert the byte to bit because you use bit here. So you can calculate that the utilization equals to this thing, and that is equals to 0.147, which is 15.7%. And the most straightforward way to compute the throughput is you got the whole throughput multiplied by the utilization, which is this one, right? And equals to 1.57 megabit per second. And this is the answer for the first question. And let's go to the second one, and it's that what received buffer needs to be at least in order to achieve a throughput of 10. So, and we also get this equation, right? And the free here indicating that the window size is free. So in here, we need to calculate that, like how many segments do we need in order to achieve the total throughput 10. So we just assume X here. Can assume. So assume X. So assume X, and then you put X here, and then you put all the rest of the values in this equation, and then this whole thing equals to 1. Equals to 100% if you want to say more correctly. And then 100% and equals to 1. And you can solve X. And X equals to 25.4. And of course, you need to scaling it to 26 because we can't have half segment, right? The numbers of segment has to be a integer, right? So this is 26. And now we also know that the size of each TCP segment equals to 1024 bytes. So we get the number of the segment equals to 1024 equals to 26,624 bytes. And this is the answer to the second questions. And for the last question, you can refer page 14. You can refer to today's lecture note, like the lecture note of this week, and the contents on page 40. Page 40, and then here you can find the average TCP throughput equals to that this 75%, right? This is 75%. And this one 8192 bytes. And RTT, of course, you know that RTT equals to double the propagation delay, which is 20 milliseconds, and then you can just put all the values in the equation here, and then you can come up with the you end up getting 2.46 megabit per second here, right? And this is pretty much for the last question. That's all about the mathematics. So all you need to do, just you grab the equation, so grab the corresponding equation and put the value and then get the result. Okay, so all good. So this is pretty much the tutorial, and can continue to tap, and if anything else you can leave, feel free to leave. All right. Oh, okay, so what question here? Question here.